In this video, we'll go over how we can define linear programs. So linear programs are always defined as a maximization or a minimization of a function that's of this form. Let's say it's a1, x1 plus a2, x2 plus all the way to, we can have n variables. So we can have an, xn plus some constant beta. So each of these AIs are real numbers. These are real coefficients. And these XIs are our variables. These are our variables that we'll later have constraints for. And beta is a real number as well. So a function of this form is known as an affine function. Just so we have some terminology, this is known as an affine function. And a linear program, you always maximize or minimize these affine functions. Now, if just another set of terminology, if beta is equal to 0 in this function, then it's known as a linear function. And this terminology will be useful when we go to define the constraints. So, again, a linear program is a maximization or a minimization of an affine function with constraints. We have a set of constraints that these variables must follow. So the constraints, they're of this form. They're a linear function that's less than or equal to some beta, some constant, or a linear function that's equal to some constant beta, or a linear function that's greater than or equal to some beta. Now, the constraints have to be a finite number. You cannot have an infinite number of constraints. And also, it's important that when you have this less than or equal to or greater than or equal to, the equal to is very important. You cannot have a constraint that's just greater than or just less than. And these functions are, again, they're linear functions. So, for example, they could be something like 5x1 plus 3x2. That's an example of a linear function. So we'll go over some examples of what are affine functions or what are linear programming functions and what are not. So the very first example is minimize x1 plus 3x2 minus 2x3 with these constraints. x1 plus x3 is less than or equal to 4, x2 plus x3 is equal to 6, and x1 and x2 have to be greater than or equal to 0. So we'll verify, is this a linear programming formulation or not? So this is a linear function, so that's good. Our minimization function is a linear function since it has real coefficients with linear terms. And our beta in this case is 0, but it doesn't have to be. It could have been a constant as well, another constant as well, and that could have been okay too. And each of these constraints, the left-hand side is a linear function, meaning the terms are linear terms with real coefficients, like, for example, 1, 1. Okay, all of these have coefficient of 1, and they have no constant. All the constants are on the left-hand side, and it's less than or equal to, and greater than or equal to. And these are all acceptable functions for our constraints. So this is an example of a linear programming formulation. Our second example is maximize x1 such that x1 is less than 10. So we'll start off with the maximization part. So that's okay. This is a linear function and it's just a maximization. So that's okay. But the problem comes here in the constraint. We have that x1 has to be less than 10. And if you remember what I mentioned previously, you can't have just less than 10. You have to have either less than or equal to 10, or greater than or equal to 10, or equal to 10. You can't just have the less than 10. And just for a rough idea, like why this is the case, this isn't the proof or anything, but just pretend that we did have this constraint that x1 is less than 10. Then when we try to maximize x1, we don't have a solution, because we might start off with, say, 9. Then we say, okay, but we can have a bigger number, that's 9.9. That's still less than 10, but that's bigger than 9. But then we can still keep making it bigger while getting infinitely closer to 10, but we'll never have a solution. So we end up in a situation where we never actually have a solution to the linear program. So that's why you can't have just less than or just greater than. And because of that, this is not a linear program formulation. So example number 3 is minimize x1 times x2 such that x1 is less than or equal to 3, x2 is less than or equal to 4. In this case, our constraints are okay. They follow a linear function on the left hand side and constants on the right hand side, and this is all just less than or equal to. That's all okay. The problem comes right here where we have minimizing x1 times x2, and since this is not an affine function where you have linear terms, this would not be considered a linear program. Our final example is maximize x1 such that x1 minus beta x2 is less than or equal to 5, where beta is the set of all is any real number between 9 and 10. So in this case, this is okay. Our maximization component, it's maximizing a single term. That's fine. But the problem comes here. The problem is we have an infinite number of constraints. So why is that the case? Well, beta can be any number between 9 and 10, any real number. So we have like x1 is minus 9, x2 is less than or equal to 5, x1 minus 9.1, x2 is less than or equal to 5, and you can have any real number right here between 9 and 10. As a result, you have an infinite number of constraints, and in a linear program, you need a finite number of constraints. Otherwise, it's not considered a linear program and you won't be able to solve it. So these are 4 examples of linear programs, and hopefully you have a better idea of how to formulate and what is considered a linear program.